Okay, we introduced security yesterday and we spoke briefly about brute force attacks, and then we had an example with the Caesar cipher. We'll go back a few slides and recap and cover in some depth the different types of attacks, and then come back to Caesar cipher and other classical ciphers. We have some model with symmetric encryption. We have a message, some plain text. We encrypt using a key and that plain text as input. The encryption algorithm produces some cipher text as output. The cipher text is sent across our communications channel. The receiver decrypts using a decryption algorithm using the same key that the source used, and if everything works correctly, gets the plain text back. The attacker, the cryptanalyst here, wants to determine the plain text and preferably the key. The plain text is nice to know because we need to know the plain text of that one ciphertext. But if we can learn the key, then we can decrypt all past ciphertexts and all future ciphertexts. So the attacker really wants to find the key as the ultimate goal. The encryption algorithms use a combination of substitution and transposition operations. We either replace one element with another or we rearrange the elements. A product system is a combination of those operations, applying them over multiple iterations. What can the attacker do? They can exploit characteristics of the algorithm. That is, if they know something about the algorithm, how it works, exploit some characteristics to intelligently deduce what the plaintext or key is. That's their goal. The other approach they have to find the plaintext and the key is to apply a brute force attack. Try every possible value of the key until you get plaintext that you recognize. Once the attacker knows the key, they can decrypt all past ciphertext that was encrypted with that key and decrypt all future ciphertexts that are encrypted with a key. So if I'm a normal user and I'm sending to someone encrypted with my key, if I don't know the attacker has found the key, I'm going to keep sending new messages using the same key. The attacker can find all those once they know the key. What information the attacker knows has an impact on how easy it is for the attacker to find the key in the plaintext. These are some classifications of different types of attacks from the perspective of how much information does the attacker know. We assume that the attacker knows the encryption algorithm and the corresponding decryption algorithm and the ciphertext. That is known to the attacker. We say that that information we assume is public. Everyone knows the algorithm is being used. Everyone knows the ciphertext, because the ciphertext is sent across some communications channel which is unsecure. If an attacker can use that information and break the cipher, that is, they can find the key or the plaintext, then that's referred to as a ciphertext-only attack. They have the algorithm and the ciphertext. If they're successful in determining the key and the plaintext from just that information, ciphertext only. Sometimes the attacker may know more information, and depending upon the algorithm, they may use that information to try to break the algorithm and find the key in that plaintext. If that's the case, then we can classify them as different types of attacks, the four here. If we know the algorithm, the ciphertext, and we also know a pair values. Then we refer to as a non-plaintext attack. That is, in the past, the user has encrypted some plaintext, and they've got the ciphertext, they've sent the ciphertext, the attacker intercepts that ciphertext, and if somehow the attacker can find out what that plaintext is, then we'd say that the attacker now has a pair of plaintext ciphertext, encrypted with some key. If they have that information, as well as the new ciphertext and the encryption algorithm, and they can use that information to find the key of the plaintext, then that's a non-plaintext attack. How does the attacker do that? So, let's try and illustrate this. Sending ciphertext to the user B. The input was saying plaintext P1. We encrypted that and we got ciphertext C1. We send the ciphertext to B and B decrypts and gets the plaintext. Those are normal users. Where C1 equals the encryption using key K of P1. Procedure. A knows key K, B knows key K. Now the attacker intercepts this. Let's say the attacker here. What do they know? In a ciphertext only attack, they know C1, they know the ciphertext. They know the encryption algorithm, E, and that's it. If the attacker can use this information and find K or P1, then that's a ciphertext only attack. A non-plaintext attack is that the attacker knows this as well as another pair of plaintext and ciphertext. Let's say P2 and C2, where C2 is equal to the encryption using key K, the same K, of P2. If the attacker now knows this, and that helps him in finding key K or plaintext P1, then we refer to that as a non-plaintext attack. They know a pair of plaintext ciphertext. They don't know the key, they know these values. How do they know this? Let's say that yesterday I sent ciphertext to B, and that was C2. That was done yesterday. And then somehow the plaintext of that ciphertext message was made public. It's no longer variable information, it's made public so that the attacker knows both C2 and the corresponding plaintext. They don't know the key, but they know the plaintext. If the attacker can use this as C1 in the encryption algorithm to find the key or P1, then we have a non-plaintext attack. So maybe a military organisation, every day they send commands to perform some operation. The central office sends commands to the army to perform some operation. The opposing military, the attacker, they're intercepting the commands which are encrypted, that is, they intercept the ciphertext. The plaintext is the commands for what operation to perform. Put a bomb here. So yesterday that ciphertext was sent, C2. The attacker couldn't decrypt that ciphertext, but after the bomb has exploded, they know what the instructions were. So they discover what the plaintext was. So in some cases, if it's possible to find what the plaintext was without knowing what the key was. If that happens, then the attacker can use that information potentially to break the cipher, to find the key and plaintext P1. The more information as we go on here that the attacker has, generally becomes easier for them to break the cipher. The next case is a chosen plaintext. Similar, but the plaintext message that they have in this pair P2C2 was actually a value chosen by the attacker. That is, let's say the attacker had created this message P2 and somehow they got A to encrypt that message with key K and send the ciphertext. Now in that case the attacker knows what P2 is because they created it and sent it to A somehow, and they know the ciphertext C2. They don't know the key. In that case, the attacker chose the plaintext. And that can make it potentially easier for the attacker to now, given P2 and C2, where P2 was chosen by the attacker, to find out what K is. If that's the case, then we call it a chosen plaintext attack. How does the attack, how do they find K? That depends upon the algorithm. But we're just trying to classify the types of attacks here, depending on what the attacker uses to perform the attack. Next one is similar, but they can choose the ciphertext as well. And the final one is when they can choose, they can have not two pairs of messages, P3 and C3 in the same manner, where they've chosen the plaintext and also chosen the ciphertext. And they use this information to discover the key. As we go over here, it generally becomes easier for the attacker to perform those attacks. The more information they have, then potentially easier to break the cipher. Most encryption algorithms today are analysed from the perspective, can they withstand a non-plaintext attack? Or can they withstand a chosen plaintext attack? Or this level? If they can withstand all types of attacks, then they would be strongest. If they could only withstand a ciphertext only attack, then that would be weaker than withstanding all of the attacks. In practice also, it's usually not just one pair of plaintext ciphertext that is known to the attacker. It can be many pairs. And in real ciphers, it can be, in theory, attacks can be performed if the attacker knows millions of pairs of plaintext ciphertext. They can use that information to work out what the key may have been. And we'll see when we look at DES and double DES, some limitations that arise there. That is, or some possibilities that the more pairs that the attacker knows, the greater the chance it is to find the key, K. So the types of attacks are usually classified based upon how much information the attacker knows. These are cryptanalytic attacks. These are not brute force attacks. These are attacks when the attacker uses some intelligent methods to work out what the key is. They don't just try every key, but they use some knowledge of the algorithm of the plaintext ciphertext pairs to work out what the key is. Like we did yesterday, where we used some knowledge of the statistics of the language to work out that the key was, I think, 5. We didn't try all keys in the second example. if something is secure. Someone designs an encryption algorithm. How do we say this is secure, this is not secure? We can say something is unconditionally secure. That is, the ciphertext does not have enough information in it, in theory, to find out what the plaintext or the key is. This is something that is secure, perfectly secure. If the ciphertext has no information that helps in finding the plaintext or the key, then if the attacker only knows the ciphertext, then they cannot derive the plaintext or the key. We'll see an example of a cipher that is unconditionally secure. It's called the one-time pad. This is perfect security. If all ciphers had this, then that would be great. The problem is that this one cipher that has this property is not very practical to use. There's a major problem with using it in practice. We'll see that one shortly. It's a very simple cipher. So unconditional security is ideal, but not achievable in practice. The only one cipher that achieves it is not very practical. All the other one ciphers are not unconditionally secure. So we need to work out some other way to measure whether a cipher is secure or not. So I can choose a cipher that is appropriate for my needs. And the way is whether it's computationally secure. And there are two things that determine if a cipher is computationally secure. The cost of breaking the cipher, that is finding the key or the plaintext, is greater than the value of the information that was encrypted. I encrypt, sorry, yeah. Sorry. It'll be easier for me too, then I can talk quieter. Can you see at the back? Is it any different? No. Okay. Not much different. used to break the cipher. Next year, it may take longer to break the cipher because computer power has gone up. So we have to put limits on whether something is computationally secure. To brute force attacks. 58-bit key. We'll just go through the alphabet. 56-bit key, we have 256 possible values. 255 attempts to do a first attack, which is 10 years if we have this ultra-fast computer. That's not so secure. And we'll give some examples later of in practice how fast a computer can actually do this. 128 bits. So it's from 4 bytes up to, what is this? 16 bytes. 16 bytes in length is the key. 7 possible attempts. It takes 1 seconds. 5 ways. This key is secure. If you find computers faster, it will be still straight up the computer will take thousands of hours to find a key. So, the key has to be secure. If computers are much faster, this is going to take a long time. 168 bits, it's from the universe. Bits, which is common for current encryption algorithms. Is the orange characters. The key and characters can be 26 characters. 26 characters length. 26 factorial possible keys. It takes 6 million years to break. Decryptions at this speed. This is secure. So, the first attack depends upon the key size. The key, the most practical it will be. Attack does not depend necessarily on the key size. It depends upon the volume and the techniques used to find a key from that algorithm. Let's just do some extra slides. is confidential information, or for example, decrypt something, quite cheap. So this hardware for less than 250,000 was this. And it could do about 8 keys per second. And it's always here's the software for key. And it does that in about 56 hours. So it does a 56-bit key in 2 days. So it's successful because at that time cryptography was quite strong. A 56-bit key was strong. So this was the case where places that could be quite cheap as well. this was 56 bits key. If it was using a same 64 bits, which would take something at a cost of $60,000. If you increase 6 bits up to 70 bits, it would cost about $10 to break it. So it's not increasing the length of the key. Each increase does required. And I think it increases the cost. If it takes twice as long to get it from the same level, you need to spend twice as much money. In 15 years' time, let's say the encryption information was to be secure for 12 years. It's encrypted with information. What's that happening for 2027, 15 years from now? It's cheap. $10,000. It's $10,000, not so cheap. So in the future, if we're using the same processor, processing power, how much traffic they can in 15 years' time is still going to be secure. Also in 15 years' time, it's still going to be secure. So it doesn't take much to get a straight basic brute force attack. used for encryption or decryption. Well, it's not practical in today's world. it's a brute force attack. 26 Ks, brute force attack, easy. 26 factorial Ks takes almost hours to do.
We have heuristic. English language.
from plaintext with the Let's look at a Playfair cipher and give you some examples to try. I'll demonstrate it with an example first.
It falls to IJ, that means you can shoot
So we can just use different keywords if that's the case. In case there is a keyword.
If it's like keyword Thailand, right? So they should only like A to X, no C, that's like only 25. So if it's more than, like Thailand is already like
So maps to I don't know, land, is it? And positions to that. Encrypting and shift position to that, and we get the right value.
Why keep 9 position?
Yes, position is positions.